तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Last few classes we were discussing about biological processes for water and wastewater treatment. We have seen that how the biological processes are working and how the waste or the organic matter whatever is present in the water and wastewater is getting removed by the microorganisms. And we have seen in detail what is an activated sludge process and what are the process modifications. We also discussed about the excess sludge production and what is the loading rate we can adopt for the activated sludge process, and we have seen what type of a process we have to go for a particular type of wastewater. For example, if the wastewater is having colloidal particles and rich in organic matter, then it is always advisable to go for contact stabilization tank, and for small communities we prefer to have extended aeration system or oxidation ditches. So today we will see what is the oxygen requirement in an activated sludge process or in any aerobic process, and what is the nutrient requirement for the microorganisms and other factors which affect the biological processes. So why oxygen is required in a biological process? The process itself is like that. The microorganisms are utilizing the organic matter whatever is present in the wastewater. So because of the air supply, what will happen? The organic matter is getting oxidized to carbon dioxide and water, and more new cells will be generated. So the oxygen requirement or the oxygen consumption rate is much more than whatever can get by natural replenishment, because the system is open to the atmosphere. So there will be definitely natural oxygen transfer taking place from the atmosphere to the wastewater or the treatment system, but that oxygen transfer is very less compared to the oxygen requirement in any system. So how can we supply this oxygen? We have to supply externally or by some mechanical means we have to supply the oxygen. So if you want to design any mechanical system for the oxygen supply or oxygen transfer, we should be able to tell that what is the oxygen requirement per unit time in the system. So how can we find out that oxygen requirement? So we can find out the total oxygen requirement by using this formula, Q into BOD influent minus BOD effluent. BOD is nothing but the biochemical oxygen requirement. So if you know what is the influent oxygen BOD and what is the effluent BOD, so whatever is the difference between the influent and effluent, that will be consumed, or that much oxygen is consumed during the process. So we have to supply that much of oxygen, and Q is the flow rate, that means this much of meter cube of water per day or per hour is coming to the system. And we also discussed that in any microbial system there are two processes, one is catabolism and another one is anabolism. In catabolism what will happen? The microorganisms will be utilizing the organic matter, and that organic matter will be undergoing a series of oxidation reduction reactions, and the energy will be liberated. This energy will be utilized for the cell maintenance, that is, or the energy liberating reactions of the cell, that is known as catabolism. And anabolism is the one which utilize the organic matter or the carbon available in the waste, and the microorganism will be creating or generating or synthesizing new cells. The energy required for this one is coming from the catabolism process, because catabolism, because of the series of oxidation reduction reactions or in the substrate level oxidation reduction, so much of energy will be liberated, and this energy will be stored in the cells in the form of ATPs, and by hydrolysis of this ATP the energy will be liberated. This energy will be utilized for the cell synthesis. So, any microbial process will be having this catabolism and anabolism. Because of anabolism, more cells will be synthesized. So, when we talk about the oxygen requirement, the organic matter whatever is getting converted to new cells, it will not be getting oxidized. For that one, oxygen is not required. So, how can we find out the total oxygen requirement in an activated sludge process? So, we can find out what is the net biomass production in the system. So, at steady state we assume that the net biomass production in the system is 0. That means amount of biomass synthesized for a given amount of time equal to amount of biomass wasted from the system. Okay, that is the steady state condition, and oxygen is not required for that part of substrate which form the biomass, because that is not undergoing any further oxidation. It will be getting more complex and the biomass will be generated. So, how can we find out what is the portion of the organic matter that is going for cell synthesis? That we can get from the yield coefficient. Yield coefficient is nothing but per unit substrate consumption. What is the biomass yield? That is the yield coefficient. So, and we know that some portion of the organic matter is going to be used for the cell synthesis. So, how can we find out what is the oxygen that is not required for this cell synthesis? Because we told that the oxygen requirement is nothing but Q into BOD influent minus BOD effluent. From that one we have to deduct this portion whatever is going for the cell synthesis. So, for that one what we have to do, we have to find out what is the general formula of a cell, and from that one we can find out what is the oxygen required for the complete oxidization of that organic compound, and if we know that that much is going as cell, okay, we can deduct that amount exactly from the oxygen requirement if the entire system is going to be getting oxidized. So, the empirical formula for biomass is reported like this: C5H7NO2. So, how can we get this one? Okay, this is based upon the CHNO analyzer, carbon, hydrogen, nitrogen, oxygen analyzer. So, you take the cell or the biomass and analyze for what is the percentage of carbon present, hydrogen present, nitrogen present and oxygen present using the CHNO analyzer. Then we can make an empirical formula. So, this is the simplest formula available for a biomass, C5H7NO2, but this is not very commonly used because we know that phosphorus is an essential element for the microbial cell. In this formula there is no phosphorus available. So, the most commonly used formula is this one, C60H87O23N12 and P. That means one biomass cell or one microbial cell will be having 60 carbon molecules, 87 hydrogen atoms, 23 oxygen atoms, 12 nitrogen atoms and 1 phosphorus. So, if you take the simple formula for the microbial cell, that means C5H7NO2. If you want to find out what is the total oxygen required for the oxidation of this cell, because we have incorporated this oxygen requirement also in the initial formula, that means Q into BOD of the influent minus BOD of the effluent. So, if we can find out what is the oxygen required for the complete oxidation of this one, that much we can deduct from the initial value, then we will be getting what is the total oxygen requirement in the system. So, if you want to find out what is the total oxygen required for the complete oxidation of this system, what we have to do? We have to convert carbon completely to carbon dioxide, hydrogen to water, nitrogen to either ammonia if you are stopping at the carbonaceous stage, and if you want to go for complete oxidation, that ammonia has to be taken or converted to nitrate. So, this will be the final formula, C5H7NO2 plus 5O2 will be giving 5 carbon dioxide plus 2 H2O plus ammonia. Here we are considering only up to this stage, we are not going for the nitrification. So, if you see this one, around 1.42 units of oxygen is required per unit biomass oxidized. If you take the molecular weight of this one, and this is equivalent to 5 into 32. So, from this one we can find out around 1.42 units of oxygen is required per unit biomass oxidized. So, in any system, if you want to find out the net oxygen requirement, that is equal to total oxygen required minus 1.42 times total biomass present in the system. And last class we have seen what is the total biomass produced in the system. So, delta O2, that means the oxygen requirement in the system is nothing but Q into S0 minus SC. S0 is the initial BOD, SC is the effluent BOD minus 1.42 times delta X, or this one we can write again like this, Q into S0 minus SC minus 1.42 into Y observed. This is the observed yield coefficient, that means total yield coefficient is there, we are taking care of the decay part, so that will be the observed yield coefficient, Y observed into Q into S0 minus SC. Or we can write in another way, delta O2 is equal to Q into S0 minus SC into 1 minus 1.42 Y plus, so if we take it as YT plus 1.42 into KD into VA into X plus NOD. So, this formula shows, okay, we are considering the Y total here, that means the what is the actual yield coefficient plus this one we are again taking, because KD into VAX is the amount of biomass what is undergoing decay or endogenous respiration, that means that biomass is getting oxidized. So, the same formula whatever we have seen earlier, we can use the same thing. So, if we want to oxidize a particular amount of biomass, then we have to supply 1.42 units of oxygen per unit of biomass, that is why this is coming like this, and NOD is the nitrogenous oxygen demand. Nitrogenous oxygen demand is ammonia, when ammonia is oxidized by in the presence of certain microorganism, what will happen, the final end product will be nitrate. So, for that one, if we have 1 unit of ammonia, we need 4.57 units of oxygen. This we will see in detail when we talk about nitrification and denitrification. What is the nitrogenous oxygen demand, we will be seeing in detail. So, total oxygen demand is nothing but Q into S0 minus SC into 1 minus 1.42 YT, this is the total yield coefficient, plus 1.42 KD VIX, KD is the decay coefficient, plus NOD, and NOD is the nitrogenous oxygen demand, and TKN0 is nothing but the total Jadal nitrogen in the effluent, which is expressed in terms of milligram per liter as nitrogen. So, if you know the total nitrogen present in the system and total BOD, that means influent BOD, effluent BOD, and if you know the biokinetic parameters like YT and KD, we can find out what is the total oxygen requirement. So, whenever we go for any aerator design, we should, that aerator should be able to supply this much of oxygen to the system at any time. So, that is the basic design criteria. Now, we will see any biological system, for the growth of microorganism we have to have nutrients, we should supply enough nutrients to the system, because the empirical microbial formula itself we have seen that carbon is present there, hydrogen is present, oxygen is present, and apart from that one nitrogen and phosphorus are there. And if you take the biomass and if you burn it, okay, we will be getting around 6 to 14% ash. This ash mainly contains phosphorus, sodium, potassium, calcium etc. or chloride, because all these nutrients or all these elements are present in micro quantities and macro quantities in microorganism. So, if the microorganisms have to grow properly, we have to supply these nutrients what is adequate for the cell growth. And whenever we take the microorganism or the sludge and if you burn it, what will happen? All the carbon will be converted to carbon dioxide, nitrogen will be converted to nitrogen gas, and hydrogen will be converted to H2O. So, remaining whatever is the ash, that is the micro and macronutrients present in the system. So, how can we find out what is the nutrient requirement in the system? So, here also we have to use the empirical formula for the microbial system. So, the most widely used molecular formula, as we have already seen, it is C60H87 O23 N12P. So, if you find out the molecular weight of this one, that means 60 into 12 plus 87 into 1 plus 23 into 6 plus 12 into 14 plus phosphorus we will be getting 1374. Okay. The molecular weight of this compound is 1374 grams. And if you want to find out what is the nitrogen fraction, it is nothing but 14 into 12. So, nitrogen fraction we can find out 14 into 12 divided by the total molecular weight, that means 0.122. That means if you take 1 gram of the biomass, it will be containing 0.122 grams of nitrogen. That means if you want to generate cells in a system apart from carbon and hydrogen and oxygen we are supplying anyway, we have to supply enough nitrogen and phosphorus to the system, otherwise the cell growth will not be proper or cell growth will not be taking place. So, if the wastewater is not having nitrogen, we have to supply nitrogen in this ratio. That means per gram of biomass generated we have to supply 0.122 grams of nitrogen, or nitrogen requirement for the entire system is equal to 0.122 into the total biomass what is going to generate in the system. And similarly we can find out what is the phosphorus requirement. So, here we can take the molecular weight of phosphorus divided by this 1374, we will be getting 0.023, and total phosphorus requirement is nothing but 0.023 into delta x, because delta x is the entire biomass going to be generated in the system or generated in the system. So, whether the nutrient requirement in a system is always a constant, it is not, and whether we have to supply these nutrients externally all the time, the answer is no, because whenever we talk about the wastewater, especially the domestic wastewater, it will be containing lot of nitrogen and phosphorus, and most of the time in excess of the requirement of the microorganism. So, we do not have to supply any nitrogen or phosphorus to the system, but whenever we go for industrial wastewater treatment, especially the system which does not have any nitrogen or phosphorus, we have to supply nitrogen and phosphorus externally. So, that is why this ratio is very important, and we have seen the ratio is 1.122 and 0.023, whether it remains a constant in a particular system. Most of the time it won't, because it is also a function of the biological sludge retention time, because when we were discussing about the process modifications of activated sludge process, we have seen that in certain systems the cell generation or the net cell production is very minimal, but in certain other systems the cell generation is very high. Example, in high rate activated sludge process, the cell generation is so high, more than 50% of the organic matter whatever we are supplying to the system is getting converted as microbial cells. But when we talk about extended aeration system, what is happening? The net cell production is 0, or the mu of the specific growth rate of the system is 0. That means the net production is 0, no microorganism is generated, or ultimately no microorganism is generated in the system. If there is no microorganism generation in the system, naturally the nutrient requirement will be almost 0, because whatever the nutrient is available in the system, initially the microorganism will be utilizing them for the synthesis of the cells, and those cells whatever is generated thus will be undergoing auto oxidation, and again the nutrients will be released to the system, and for the new cell synthesis the same nutrients will be available. So, the net nutrient requirement for the system will be 0. So, that is what this graph shows, okay, how the nitrogen, phosphorus and BOD ratio changes with respect to biological sludge retention time. As the biological sludge retention time increases, we can see here, okay, BOD is to nitrogen is to phosphorus ratio also increases. Okay. If the BSRT is very low, that means just like in high rate activated sludge process, the BOD is to nitrogen is to phosphorus ratio is 50 is to 5.4 is to 1. That means we have to supply more nitrogen and phosphorus compared to the BOD. But as the BSRT increase, we can see that it is coming 100 is to 5.4 is to 1, then 150 is to 5.4 is to 1, and 200 is to 5.4 is to 1. Okay. So, depending upon the process modifications or depending upon the nature of the process we are choosing, the nutrient requirement also will change. So, when we talk about the nutrient requirement and the nutrient present in the system, okay, depending upon the requirement we can select the process according to our convenience. What I mean is, if some industrial wastewater is there and there is not sufficient nutrients present in the system and external addition of this nutrient is costly, so we can go for a system which requires least nutrients, that means extended aeration system. Okay. So, depending upon the nutrient availability and the requirement, we can make the choice according to our convenience. Now, we will talk about the solid liquid separation process in an activated sludge process. We have seen that in activated sludge process, okay, unless the solid liquid separation is there, we cannot call it as a treatment process, because in aeration tank only the conversion of soluble COD or soluble BOD to colloidal solid or colloidal BOD is taking place, because the organic matter or whatever is present in the system is getting converted to new microbial cells, and that new cells will be remaining in the system. So, if you take the BOD of the sample from the aeration tank, it will be almost same as that of the influent. Okay. Some reduction will be there, because whatever is getting oxidized for the catabolism process, okay, whatever is converting to carbon dioxide and water during the catabolism process, that much of reduction will be there in the BOD, but whatever is converted into cell, okay, it will be remaining in the system and that will be contributing to the BOD. So, if you would not have a sedimentation tank after the aeration tank, okay, your treatment efficiency will be very, very less in an activated sludge process. So, solid liquid separation process is very, very essential in an activated sludge process. And we have seen that the microbial growth stage is also important for this solid liquid separation process, because if the microorganisms are in the low growth phase, what will happen? Okay, they will be staying as discrete particles, or the flocculation of the particles is almost impossible. But if they come to the stationary phase or endogenous respiration phase, or the end of the stationary phase, the microorganism start secreting or producing extracellular polymers that will be acting as natural biopolymers, which enhances the flocculation of the system or flocculation of the microbial cells. Once the flocculation takes place, then it is very easy for the solid liquid separation process. Now, we will see in detail how can we design a solid liquid separation system for an activated sludge process. Okay. So, when we come to the sedimentation tank design for an activated sludge process or the secondary sedimentation tank design, we have to meet two criteria. One is to produce clear effluent to meet the effluent discharge standards. The second one is to concentrate the biological solid to minimize the quantity of sludge that must be handled. So, whenever we go for the design, these two objectives should be satisfied. So, how can we satisfy these two objectives? The clarification is based upon how fast the particles are settling, but the thickening is entirely different from that one, because it will be settling fast, but the settled sludge volume, if it is very high, then the sludge handling will be so difficult. Moreover, whatever the sludge generated in the activated sludge process, it is active biomass. So, we cannot discharge them to the sludge drying bed. We have to go for further treatment which can stabilize the sludge. So, it is always advisable to have the minimum volume of the sludge. Then we can reduce the volume of the sludge digester or any further treatment whatever we are proposing to take care of the sludge. So, now we will see in detail how can we go for the design of the secondary sedimentation tank to meet these two objectives, that means clarification as well as sludge thickening. In the initial classes we discussed, okay, the settling can be classified into 4 different categories. One is type 1 settling, second one is type 2 settling, then zone settling and compression settling. So, whenever we talk about the secondary sedimentation tank of an activated sludge process, the sedimentation tank or the settling is coming under zone settling and compression settling. Zone settling is taking place when we talk about the clarification, and compression settling is coming into picture when we talk about the sludge thickening. Here sound settling is taking place because the particles whatever is present or whatever is coming to the secondary sedimentation tank is flocculent in nature, and if we see the concentration of the particle, it is very high, because we discussed already that the MLSS concentration in a conventional activated sludge process varies from 2000 to 5000 milligram per liter. So, the concentration of the suspension is relatively high and the particles are flocculent in nature. Biomass concentration varies from 2000 to 5000 milligrams per liter and they are flocculent in nature. So, concentrated suspension of flocculent particles. So, it is coming under type 3 or sound settling. So, how can we go about for the design? Here also we have to conduct the batch analysis. How can we conduct the batch analysis? The batch analysis can be conducted in measuring cylinders or small settling columns. This is a settling column. So, what we have to do is first fill the settling column with the sludge of the sludge which is having the same concentration as that of the activated sludge process, say 2000 to 5000 milligram per liter. So, the sludge we are taking here and this is the time. So, what we have to do after that, with respect to time, find out what is the position of this sludge. So, we will be observing different zones in the settling. This is the this A portion, this is the clarified zone, and another zone will be there which will always maintain the same concentration of that of the sludge whatever we are introduced in the first column, and we will be having a compression or thickening zone here, and the bottommost portion is the compression zone. So, with respect to time, what we have to see is we have to find out what is the depth of this clarified zone. That means we will be having a very clear zone as well as a zone which is having the same thickness of the particles as we have introduced. So, we will be taking the depth of that clarified zone with respect to time till there is no decrease in the depth or there is no increase in the depth of the clarified zone. So, here it is very clear. This is the initial stage when the initial concentration of the particle is equal to C naught. After time t1, what is happening? The clarified zone is coming up to here and entire sludge is settling as a zones, as a blanket. That is why it is known as zone settling. So, the clarified zone is coming up to here. So, we know what is this height, what is the height of this clarified zone. Then at T2 again we are taking the height of the clarified zone, and like that we are going on, and after some time we can see that this depth is not increasing considerably or the curve is becoming almost flat. So, this information we can use for the design of the clariflocculator. That means this portion, this clarified zone is representing, okay, how can we get the clear effluent from the settling tank, and this portion will tell us how much concentrated sludge we can produce using the settling column or using the sedimentation tank, because we are using the same data for the design of the sedimentation tank. So, it will be able to tell us what is the effluent quality or what is the area required for getting the effluent quality and what is the area required for getting the desired sludge concentration. So, we will go into the detail of the analysis. So, I have already discussed what are the different zones visible in the settling column analysis. A is the clarified zone, B is the zone where initial concentration C naught is preserved. That means always that same concentration will be there, and C is the thickening zone and D is the compression zone. So, if you put different concentrations of the sludge in the settling column, okay, because I have told you whatever sedimentation tank we have to design, okay, we have to take the same sludge concentration as that in the aeration tank for which we are going to design the sedimentation tank. So, if the sludge, we have seen that the sludge concentration can vary from 2000 to 5000. So, what will happen if the sludge concentration varies? The settling column experiment or the curve's nature will be something like this. If the concentration is very low, the initial settling will be very fast. So, you will be getting a curve something like this. As the concentration increases, the curve will be coming like this. Okay. Here we can see C4, this is having maximum concentration and C1 is having the least concentration. So, if the sludge is having less concentration, the clarification will be very fast, okay, because this is the slope that gives the settling velocity of the particles. Now, if we have the settling column analysis data, because we will be doing the experiment with a particular concentration. So, finally, we will be getting a curve something like this, initial portion, and this is the portion which where the compression is taking place, and it will be becoming asymptotic to the x-axis. So, what we have to do is draw tangents to this straight line portion and this asymptotic portion. So, that will be meeting at a point, say here O, okay. Here the O point is coming by drawing tangents to the top portion where it is straight line, okay. Draw a tangent to this portion and draw a tangent to this asymptotic portion, that will be meeting at a point here, say point O. Then draw an angular bisector to this point, that will be meeting the curve at point A. Then draw a tangent to this line, tangent to this curve through the point A. So, this is the tangent. Now, using these informations, how can we design the system, okay. In this curve itself, we can see different portions, okay. This portion, the straight line portion, that is not that gives the hindered settling, or if you take the slope of this portion, that will give you the hindered settling velocity, that is VH. This velocity is very important for the design of the sedimentation tank for the clarification purpose, and this is the transition zone and this is the compression zone. So, now we have this point A, and we have the tangent, okay, and we have the initial height of the settling column. Now, how can we go about, okay. Area of the clarifier is nothing but Q by VH, that is the area. Q is the flow rate and VH is the hindered settling velocity. So, we can find out what is the area required, okay. At the point of intersection of tangent from the hindered settling zone and compression settling zone, draw an angular bisector which meet the curve at A. So, this already discussed. Now, how can we go ahead? We have to make the mass balance of the entire system, because we know that initially the concentration of the sludge was C0, that means say it is in between 2000 to 5000 milligram per liter, and the total height of the sludge volume was say H0, that means that is the height of the settling column. But after a particular time, what is happening? The entire zone will be settling, or entire sludge will be settling, and you will be getting a considerable amount of clear water, and entire sludge will be occupying only a small volume, say HU, that we can find out from the system, and Cu is the concentration at that time. So, how can we find out HU? HU is equal to C0 H0 by Cu, because at any time C0 H0 is equal to Cu HU. We are not removing anything from the system. So, total sludge volume will be remaining as a constant. And how can we get Cu? Cu will be your design sludge concentration. So, from this one we can find out what is the HU value. HU is nothing but C0 H0 by Cu. Cu is what is the desired sludge concentration we need from the secondary clarifier. So, HU is available. Then what we have to do? This is your HU. So, you mark it in HU. Then draw a horizontal line through HU, okay, and we will be getting a point where the tangent which is drawn through this A meeting this horizontal line, say B, okay. So, from B drop a perpendicular that will be meeting your time axis at TU, okay. So, this is the time required for that much of sludge thickening to take place. So, if you want to find out the velocity of thickening, okay, because we have seen what is the hindered settling velocity and we have seen what is the area required for the clarification purpose. So, now we have to find out what is the area required if we want to get a particular amount of thickening. So, the velocity of thickening or thickness is equal to HU by TU, because HU is the height and TU is the time available. So, velocity is nothing but the distance by time. So, we get the VTH, this is nothing but velocity of thickening. So, we can find out what is the area of thickener required. Area of thickener is nothing but Q divided by velocity of thickening. So, we got two areas, one is A for thickening and one is A for clarification. So, two areas are there. So, compare these two area, and if you want to meet both the purposes, we have to provide the area which is maximum. Then only we will be able to meet both the criteria. Another way of finding on the area is continuous flow analysis, because in batch system we are not considering any underflow, but in any conventional activated sludge process we take, the sedimentation tank will be operating in a continuous mode and the sludge will be withdrawing in a continuous mode. So, there will be always the effluent going from the system, and there will be always sludge collected from the bottom of the tank. So, two forces are acting on the sludge. Because of this withdrawal of the sludge, there will be some velocity with which the sludge will be coming down, and another one is the weight of the particle, or because of the gravity force some thickening will be taking place. So, if you want to take both the things into account, okay, we can use the flux theory for the design of the secondary sedimentation tank. So, what is this solid flux theory says? So, before going into the solid flux theory, we will discuss what is solid flux. Solid flux is nothing but the mass of solids per unit time passing through a unit area perpendicular to the direction of flow. That means the amount of particle or mass of the particle passing perpendicular to the cross sectional area at a given time, that is the solid flux. So, whenever we talk about a sedimentation tank which is having underflow constantly, then the flux will be because of the underflow velocity as well as because of gravity. So, we have to consider both the things together. So, product of solid concentration and velocity gives you the solid flux. So, downward velocity, as I have already discussed, it is having two components, the transport velocity due to the withdrawal of the sludge and the gravity settling of the solids relative to the water. So, transport velocity, it is a function of underflow rate and area of the tank, okay, because your sludge withdrawal pipe will be having much lesser diameter compared to the sludge thickener. So, the underflow concentration will be depending upon the underflow velocity, because velocity will be calculated based upon the pipe diameter with which we are withdrawing the sludge, and the area of the clarifier, because the flux is nothing but what is passing through a unit cross sectional area in the perpendicular direction. So, if the clarifier area is small, then the flux will be less. So, the transport velocity Vu we can calculate using this formula. Vu is equal to Qu divided by area, where Q is the underflow rate. So, solid flux due to underflow we can write like this: Gu is equal to Vu into Xi, that is nothing but Qu by A into Xi. Xi is the concentration of the sludge, whatever is present in the tank, and Qu is the flow rate, and A is the area of cross section. And we have already seen that solid flux is solid flux due to gravity we can calculate using Gg, using this formula. Gg is equal to Vg into Xi, and Vg is the velocity because of the gravity. So, total solid flux Gt is equal to Gu plus Gg. I will explain once again. We have a clarifier where the underflow is also taking place, and we know what is the rate at which the sludge is withdrawing from the sedimentation tank, and the sludge is settling down, and because of the sludge weight itself there will be some settling velocity, that is known as the gravity velocity. So, whenever we consider the sludge settling, there are two components, one is because of the underflow and another one is because of the gravity. So, the total solid flux, whenever we consider a particular cross section, the total solid flux is the sum of the solid flux due to the underflow and the solid flux due to the gravity. Solid flux due to gravity can be calculated using this formula Vg into Xi, where Vg is the velocity due to gravity, and xi is the concentration of the sludge, and gu is nothing but vu into xi. Vu is the underflow velocity, that is qu by a. Now, how can we go around for the design? Okay, we can use graphical method. There is analytical solution also to find out what is the area required to achieve a given sludge thickening. So, here the y axis gives the solid flux. Solid flux is nothing but the sum of the gravity flux and the flux due to underflow, and here we can get the solid concentration. So, this line, this gives the solid flux due to underflow, because Vu is a constant and xi is keep on increasing. So, you will be getting a line something similar to this one, okay, and this is the solid flux due to gravity. So, what will happen? Okay, initially it is low, then it is increasing, then it is decreasing. Why this particular shape is coming? Because initially the concentration of the solids are high, relatively low compared to these portions, but the settling velocity or the velocity, gravity velocity is high. So, the flux is nothing but the product of concentration and the velocity. So, here the value will be relatively low, but as the concentration increase, okay, the reduction in the velocity is not so considerable compared to the increase in the concentration. So, naturally the product will be high. So, that will be continuing for certain extent for a particular value of xi. Then afterwards what will happen? Though the concentration of the sludge increases, the velocity with which it is compressing will be decreasing. The reason is the sludge is so thick, so it is not able to compress it much more. So, the velocity with which it is compressing or with which it is settling will be very, very less. So, naturally the product of Vi and Xi is coming down, that is why this portion, and finally it will be becoming almost asymptotic like this. Then now we will see how the total flux will be looking like. So, this is the flux due to underflow transport, because Vu is remaining as a constant and Xi is keep on increasing. So, you will be getting a straight line something like this, and this is the gravity flux. So, the total, if you take gravity flux plus underflow transport, we will be getting this point here, that corresponding to this distance plus this height. So, that is the total flux. So, we will be getting a total flux curve something like this. So, how can we use this data for the design of a secondary sedimentation tank? Yoshika suggested a easy graphical solution method for this solid flux using graphical method. What he has done is, he has taken the gravity flux alone, okay, by considering the similar triangle theory. So, your gravity flux is coming something like this, and underflow or the flux due to underflow is coming like this, okay, and if you take the sum of these two things, you will be getting the same thing, okay. So, here the triangle was like this and your gravity flux was like this. So, take the same triangle in this side, okay. So, you will be getting the underflow transport like this and the gravity flux like this. Now, how to use this information for the design? Say we want to get an underflow concentration of xu1, that means this much is the sludge concentration we need when we withdraw the sludge from the thickener. So, what we have to do is, you have the gravity flux line here, draw a tangent to this gravity sludge line, gravity flux line. So, it will be passing through, touching this point, and it will be cutting the solid flux line at some point, okay. For different concentrations we will be getting different points. For xu1 you will be getting GL1, and xu2 you will be getting GL2, and xu3 you will be getting GL3. So, this GL1, GL2, GL3, it is known as the limiting solid flux, that is the maximum flux we can get for that underflow concentration. So, using this information, okay, we can find out what is the area required for the secondary sedimentation tank. So, we know what is the total solids coming to the system, we know what is the flow rate Q, and we know what is the sludge concentration in the influent. So, we can find out what is the total solid loading to the sedimentation time. So, if you know the total solid loading to the system and the unit of this solid flux is kilogram per hour per meter square, that means kilogram per time and area. So, if you know total solid loading and the limiting solid flux, okay, we can find out what is the area required. And one interesting thing from this graph is, okay, so we are drawing a tangent here, and where the point is, where this line is meeting the gravity flux curve. If you find out what is the solid flux corresponding to that one, that will give you the gravity solid flux, okay, and this portion will give you the solid flux due to underflow. Okay. So, this is very important. This is the gravity solid flux and this is the solid flux due to underflow. So, we can find out what is the area required, and the area required for the clarifier for the clarification purpose we can get from the hindered settling velocity. So, the summary of this one, secondary clarifier design, the important objectives are effluent clarification and sludge thickening, conduct laboratory experiments and get necessary data. Based on this one, do the design. Now, we will see, okay, we have seen now what is the nutrient requirement, what is the sludge production and what is the loading rate required and how much is the oxygen required and how can we separate the solids and liquid in a activated sludge process. Now, we have to discuss, okay, how can we supply the oxygen required for the activated sludge process, because unless enough oxygen is supplied to the system performance will be coming down drastically, because we have calculated what is the total amount of oxygen required, that is nothing but Q into S0 minus SC, that means the flow rate multiplied by what is the BOD removed in the system minus whatever is converted into the biomass. So, what is the requirement of aeration? Okay, oxygen utilization rate of the activated sludge process is much higher compared to the oxygen whatever is transferring to the system. The rate at which microorganism in the biological reactor consume oxygen is known as oxygen utilization rate, or it is known as OUR. And in any activated sludge process, oxygen utilization rate is always higher than the natural replenishment rate. Hence, artificial aeration is essential, because we have to meet the oxygen utilization rate in whatever way we can to get the maximum efficiency. So, natural aeration will not be able to provide that rate. So, what is the other way? We have to go for some mechanical devices. So, we will discuss in detail what all are the requirement in the oxygen for different systems of activated sludge process or different modifications of activated sludge process. When we talk about extended aeration system, we have to supply around 10 milligram per liter per hour oxygen. That means oxygen consumption rate per time is less in extended aeration system. In conventional activated sludge process, oxygen utilization rate is 30 milligram per liter per hour, and high rate activated sludge process, the oxygen utilization rate is 100 milligrams per liter per hour. So, we should provide the system which is able to supply this much of oxygen in the given time. So, for this purpose we are using aerators. Okay. Aerators are the mechanical devices which can supply the required amount of oxygen for an activated sludge process. And aerators can be of two different types. One is diffused aerators and another one is mechanical aerators. We usually go for diffused aerators in plug flow system and mechanical aerators in conventional activated sludge process where it is a completely stirred tank reactor system. So, these are the pictures of certain aerators. This is a diffused aerator. We can see that oxygen is coming out from the diffuser and it is going like this, and it is taking a path something similar to this one. Okay. It is going like this, coming like this. So, entire area will be getting oxygenated. This shows a surface aerator. We can see this is the surface aerator and the water is getting mixed thoroughly here. The turbulence available here is much higher compared to the plug flow or the diffused aerator. So, here well mixing is taking place, moreover oxygen transfer is also taking place. So, in any activated sludge process aeration tank, we provide a series of aerators. Here we can see 1, 2, 3 aerators. So, depending upon the oxygen requirement and oxygen transfer rate of these aerators, we can design or we can find out how many aerators we have to see, and depending upon the influence zone of the aerators, we can find out how should we place the aerators. Okay, this is also some other pictures of aerators. Okay, so how can we design the aeration facility? The objective of the aeration facility is to provide calculated oxygen demand and to provide adequate mixing. And DO concentration in aeration tank, in conventional activated sludge process, we are supposed to maintain a dissolved oxygen concentration of 0.5 to 1 milligram per liter, whereas in extended aeration system we are supposed to maintain a dissolved oxygen concentration of 1 to 2 milligram per liter. So, your aeration facility, whatever you are going to provide, should be able to give this much of dissolved oxygen concentration in the system. So, and now when we talk about the aerators, the aeration itself is very important, and how the air is getting transferred from the atmosphere to the water. Okay, there are many rate limiting steps present, okay, and there are many factors affecting this, affecting the transfer of oxygen from the atmosphere to the wastewater. The most important things are the turbulence, the temperature, the wastewater characteristics. All these things are very important. And another one is the oxygen saturation limit. Okay, if your wastewater oxygen content is very low and your atmospheric oxygen content is very high, that we all know. So, if the concentration gradient available is very high, then naturally the oxygen transfer will be very fast. Similarly, if the temperature is low, oxygen transfer will be high, and if the temperature is high, oxygen transfer will be low. And another parameter is the wastewater characteristics, because what will happen in wastewater, there are many compounds or many pollutants present in the wastewater. So, some of these compounds are hydrophilic in nature and some are hydrophobic in nature. Hydrophilic molecules will have always a tendency to be in the liquid or be in the water, and hydrophobic particles will be trying to come out of the system. So, if the hydrophobic particles are more in the system, what will happen? That will be forming a thin layer of these particles above the liquid surface. So, when that liquid surface layer is there, naturally other molecule transfer will be hindered. So, if the wastewater is having lot of solids or lot of hydrophobic solids, then naturally the aeration rate will be getting affected. And the fourth important point is turbulence. If you create more and more turbulence, the oxygen transfer will be more, but if the turbulence is very less or the water surface is quiescent, then what will happen? The oxygen transfer will be less. Okay. So, we will discuss about this aeration in the next class. So, now we will see what are the things we have discussed today. So, we have seen that how can we calculate the oxygen requirement in an activated sludge process, that is nothing but the BOD consumed in the system, but we do not have to supply oxygen for the cell synthesis. So, whatever amount of waste is converted into cell mass, okay, that much oxygen requirement we can deduct from the system. So, total oxygen is the sum of the BOD removed minus 1.42 times the cell synthesized plus 1.42 times whatever is the cell decayed in the system plus whatever is the oxygen required for nitrogenous substances, because if organic nitrogen or ammonia nitrogen is present in the system, that will require some oxygen for the complete oxidation. Ammonia will be getting oxidized to nitrate. So, each unit of ammonia requires around 4.57 units of oxygen for the complete removal. Then we were discussing about what is the nutrient requirement, because the microorganism requires micronutrients and macronutrients for their growth. In wastewater, most of the time these nutrients are present in plenty, so we do not have to supply them externally. But when we talk about some wastewater which is especially coming from industries, they may not be having all these nutrients. So, we should know what is the nutrient requirement for the system, and we also seen that this nutrient requirement is not a constant, it depends upon the type of or the modified activated sludge process which we have selected. If the BSRT is high, then BOD is to nitrogen is to phosphorus ratio is high. That means for high BOD we need, means the nitrogen phosphorus requirement is less, but if the BSRT is less, that means more and more cells will be synthesized in the system. At that time we have to give more and more nutrients. That is why high rate activated sludge requires more nutrients compared to extended aeration system. Then we have seen how to design a secondary sedimentation tank for an activated sludge process. It is based upon two concepts or two objectives has to be satisfied. Those are one, clarification and sludge thickening. Clarification, the area required for the clarification purpose can be calculated based upon hindered settling velocity, and the area required for the thickening can be calculated based upon the batch column studies or by flux theory. Flux theory, we are considering the flux due to underflow as well as gravity, and using the graphical method we can find out what is the limiting solid flux, and for a system we know what is the sludge loading per day or per hour coming, and by dividing the limiting flux we will be getting what is the area required.